Welcome back. This is part 3 of our video on intermolecular forces. So now we're going to focus on dipole-induced dipole. What that means is when you have a nonpolar molecule that will interact with a polar molecule. This is much weaker than dipole or ion dipole because you've got this nonpolar molecule. Now what will happen is that as a polar molecule such as water approaches a nonpolar molecule, its negative charge will begin to repel electrons that are evenly distributed in the polar molecule. And as they repel the electrons, they force the electrons to move over to the other side of the molecule. And so what you'll see is instead of this even distribution of electrons, the electrons are more distributed on one end temporarily than the other. So we call this a temporary dipole because it only happens while the water molecule or other polar molecule is nearby. As soon as that molecule moves away, everything shifts back over to being an even distribution and having no dipole. But for this temporary time while it's nearby, since its repulsion pushes the electrons to one side over here, this side of it takes on a temporary positive charge, and this side takes on a temporary negative charge. While it has that temporary dipole, other molecules can come in and begin to be attracted to it. Now this is a much weaker force than the others, so the amount that they can interact is relatively small, but it does have some really important real-life implications. So again, generally this will only occur if the nonpolar molecule contains some level of highly electronegative atoms that are symmetrical in shape. So for instance, oxygen molecules, O2, have two really electronegative atoms, but they are symmetrical. That's a nonpolar bond, so the molecule is nonpolar. And so when a water molecule comes in, it pushes the electrons that are located on one of the oxygens over, inducing the dipole. So we call this dipole-induced dipole because the induction occurs because there's a polar molecule involved. So oxygen molecules, carbon dioxide molecules, nitrogen molecules, all of those are examples of atoms that contain highly electronegative atoms that are symmetrical, so they're nonpolar, but can be induced into a dipole by the interaction with another polar molecule. So these nonpolar gases with lone pairs that can be induced are super important because they're the gases that are necessary for life. We know that oxygen is critical for all biological organisms. Carbon dioxide is necessary for things like photosynthesis and so forth. So these gases are able to dissolve in water at very low levels due to the induced dipoles. Now this is really important because, for instance, if you're a fish and you live in the ocean, if you live in a lake, you need to be able to extract these small number of dissolved oxygen molecules out of the water for your respiration. If induced dipoles did not exist, there would be no dissolved oxygen in water, and there would be no life in the oceans. And if there were no life in the oceans, we would have never had life on land either. So whenever you open up a soda and you see the bubbles of carbon dioxide gas that are forming out of it, that's because those carbon dioxide molecules had been dissolved into the water. Now, the amount that can be dissolved in is really low. So this is the solubility of grams of carbon dioxide into 100 grams of water. So you can see on here at 0 degrees Celsius, which is near freezing, only about 0.3 grams of carbon dioxide can be dissolved for every 100 grams of water. That's not very much. And one thing you'll notice, though, is that as you increase the temperature, you decrease the solubility. As you increase the temperature, you decrease how much of that gas can dissolve into solution. So I want you to think about this for a second, and think about this in terms of kinetic theory. Why can more gas dissolve in cold water than warm water? What's going on with the motion of the molecules when things are cold versus when things are warm? Take a moment to think about that. Pause the video if you need to. So if you think about what's going on is as you heat up the molecules, they start moving faster and faster and faster. And as the gas molecules that are dissolved in the liquid start moving faster and faster and faster, they can have enough kinetic energy to overcome these weak dipole-induced dipole forces and escape as a gas. And so the faster the molecules are moving, the less they can be held into the liquid and the more likely they are to escape the liquid and go back into the atmosphere. And so the solubility of all polar gas, non-polar gases like oxygen and CO2 and nitrogen goes down with increasing temperatures. This has huge implications for life on Earth. So you've probably noticed before that if you take a cold soda out of the fridge and you pour it into a glass, there's bubbles coming out. That's the carbon dioxide that's escaping into the atmosphere, but it's not that many bubbles. And the bubbles will start to form on the glass, and you may get a little fizz. But if you take a warm bottle and you were to pour that into the cup, it fizzes enormously. That is because warmer liquids hold less dissolved gases than colder liquids. And so as long as it's sealed in the bottle, it's under pressure, the gases can't go anywhere, they can't escape the liquid, but as soon as you open that cap, boom, those gases are coming out, as you can see right here. So, cold liquids hold more dissolved gases than warm liquids. Now, why is that important beyond just, when to open your soda? Because oxygen is a limiting resource for aquatic organisms. Oxygen is at such low levels in the water that fish are literally at risk of suffocation in their environment. Think about that for a second. Here in the air, there is so much oxygen in the atmosphere that we are never at risk of suffocation, of losing our source of oxygen. However, in water environments, the amount of oxygen dissolved in the water is so tiny that fish are always at risk of losing access to that dissolved oxygen. And the higher the temperature goes, the less dissolved oxygen there is, to the point where they can use it up. So there's a rule of thumb if you ever have fish at home, which is 1 inch of fish per gallon of water. So if you have a 10-gallon tank, you should have no more than 10 inches worth of fish, whether that be 10 small little fish or 1 big fish. You should never have more than 10 inches of fish in a 10-gallon tank. Now, you've probably, if you've ever had a fish tank, probably seen these little bubblers that we have. What do you think those bubblers are for? Well, one of the things you have to realize is that the fish are using up the oxygen that's in the tank. And if you didn't have the bubbler, essentially what would happen is the fish would use up the oxygen, and it wouldn't be able to dissolve in from the air as rapidly as it's being used up, and the fish would literally suffocate. But by using the bubbler, you're adding more oxygen back into the water, helping the speed of the dissolving of the oxygen back into the water, helping to speed up that reaction, and you're hoping to keep an equilibrium where the fish using it up is equal to the amount dissolving back into solution. Now, in environments where water temperatures can change dramatically with the seasons, what you often will see are massive summer fish die-offs, where basically as a lake begins heating up, the dissolved oxygen level goes down, and if it goes down low enough, say when water temperatures reach 90 degrees in the desert, the fish suddenly do not have enough oxygen to survive and they all suffocate, and then they all bubble up to the surface and float out and rot on our beaches, and it gets really stinky, and it's very unfortunate for the fish as well. So these summer die-offs are actually a common occurrence in certain areas where water temperatures can increase dramatically over the course of a summer. Once water temperatures cool in the fall and winter, then dissolved oxygen levels go up and the fish are then safe for another season. Take a look at this graph, or this map here. This map shows the amount of ocean productivity. In other words, how many living organisms are in the water. And what you'll notice here is that the areas that are red are extremely productive. They have a lot of things living in the ocean, while the areas that are purple and blue are very low productivity. So think about that for a minute. Like, what's going on with that pattern? Why are there a lot more fish and other living organisms in the far northern oceans, like the North Atlantic and North Pacific, as well as along Antarctica, than there is out here in the tropical regions of our oceans? Well, if you think about it, the further north you go, the colder the water gets. And the colder the water gets, the more dissolved oxygen is in the water. Not only that, the colder the water gets, the more carbon dioxide can dissolve into the water. Carbon dioxide promotes photosynthesis, so algae and phytoplankton can bloom. Increased dissolved oxygen allows for the fish to survive, and they can feed on this increased amount of plankton. And so these northern oceans are a lot more productive than the southern oceans. If we look at this map here, you can see the currents and what impact they can have. So the currents go clockwise in the northern hemisphere, and so in the east coast you have what's called the Gulf Stream, where warm tropical waters go up the east coast and then turn and start heading out. That brings warm temperatures and humid conditions throughout the southeastern United States, and it also means that the water itself has lower amounts of dissolved oxygen. However, down our west coast, we have something called the California current, which brings cold water down from Alaska. This cold water is high in oxygen, which means it can be very productive for marine organisms. So you'll notice on our west coast, first of all, it's cold all year long. So even in the heat of the summer, if it's a 90-degree day, if you try to go swimming in the Puget Sound, if you try to go swimming in California, the water's freezing cold. And that's because of this cold water coming down from Alaska. But our waters are extremely productive and very good for fishermen. And so you'll notice that marine life on our beaches and our tide pools out in the ocean are much higher than you're going to find out on the East Coast, where basically your beaches are almost devoid of life, it seems, in many cases. So as we look here, you'll notice that you've got these extremely productive environments in the area of Alaska. How many of you have ever seen that show, The Deadliest Catch? Yeah, I know you did. So where are they doing that? They're doing it up in Alaska, where all of this bright red productivity is. So these guys go up there and risk their lives in some of the most dangerous waters on Earth. In fact, crab fishing is considered one of the top 10 most dangerous jobs in America. And they go up there into these extremely dangerous, stormy waters because they're cold, and that means they're productive. And there's huge amounts of marine life up there. That's where so much of our fish in the United States is caught, is up in that Alaska area. The North Pacific as well. Places like Iceland and Norway are famous for their productive fish catches. Now, as you look at this, you'll notice that there are a few areas where the oceans are productive that are not in the Arctic, but rather are in more tropical locations, like here off the coast of Africa, off the coast of South America. What is going on in these tropical waters that can allow them to be productive even though water temperatures are really warm? Well, there's two things. First of all, there's a lot of nutrients that you're going to see that happening right near shore, because right near shore, two things happen. First of all, there's rivers that feed nutrients into the water. And second of all, you've got wave action. As the waves come in and hit the shoreline, hit the coral reefs, that water is churning around and it's helping to dissolve more oxygen into the water, almost like that bubbler in your fish tank. And so that allows for more marine organisms to live right near the shore. So what you'll often find is that the coral reefs right near shore are extremely productive and produce lots of fish and are important to the economy of those areas. But you go a few miles offshore and it becomes what is known as the ocean desert. Warm water that is low in productivity, low in the number of fish. In fact, if you're out in the open ocean, you could probably go days without ever seeing a fish because there's so little out there. Okay, we'll do dispersion in our final video.